Welcome to Technology Works. I'm Brad Braufman, and today we're going to go spinning up, and away for a brief look at the science of helicopters. As far as technologies go, helicopters are in a class by themselves. At once crude and sophisticated, obvious and inconceivable. They're like the great fire-breathing dragons of fairy tale lore. They can't possibly exist, and yet they're everywhere. Of course, the essence of helicopter is levitation. That ability to lift up out of your parking space, hover at will, go take care of business, and then return to Earth in gentle, dramatic fashion. It took many years to be able to fly like that. In 400 BC, the Chinese invented this flying top. It's still available in toy stores today, and you'll also find it at the core of every helicopter that's ever been built. This one was made in China, and it's just as flighty as ever. But it's inspired dreamers and aviation enthusiasts for over 2 millennia. In 1484, Leonardo da Vinci supersized the design to accommodate passengers. This is really just the wild child of his imagination, but it helped cast the dream of vertical flight onto a human scale. 300 years later, a Frenchman tricked out the Chinese whirligig with feathered propellers for improved performance, dual counter-rotating hubs for stability, and this great bow-shaped starter pulley for clean launches. Despite a rather whimsical appearance, this was a landmark design based on sound engineering principles and scientific research. Fortunately, that trend continued, and the early aviation pioneers overcame 6 fundamental challenges in their quest for vertical flight. The first of those was power. Remember those magnificent men in their flying machines? No one ever seemed to have enough power to get up off the ground. By the early 1900s, though, aircraft engines had become efficient enough to lift more than their own weight, and the door was open for powered flight. The second challenge was lift. Helicopters rely on spinning wings, called rotors, in order to generate lift. Let's see how that works up close. I'll get out my big demonstration model for a wing, and as I sweep it forward, you'll notice that the air tends to push it up. That's the force of lift in action. Now we can explain this effect in 2 different ways, using either Newton's third law of motion or Bernoulli's principle. They're both equally valid, they're just different interpretations or models to help us understand what's going on. Newton's action-reaction deal is pretty easy to see here. I sweep the wing forward, and it pushes down on the air, forcing it out of the way. But the air doesn't really want to move, so it reacts. It pushes back up against the wing, and we get lift. Now this flat plate is a pretty crude wing, but eventually engineers developed a much more efficient shape called an airfoil. Let's look and see how the air flows around that design. Watching the airflow here raises some pretty interesting questions, which brings us to Bernoulli. Bernoulli discovered that faster moving air is less dense and has lower pressure than slow moving air. Now you've probably experienced this when you're driving in the highway. The faster moving traffic tends to spread out. It gets less dense. Then there's an accident. Cars slow down, bunch up, traffic gets more dense. We can see Bernoulli at work in our airflow animation. Notice how this looks like 2 parallel flows of traffic. The one below the wing experiences a lane drop, so the air slows down, gets compressed, and pushes up against the wing. Meanwhile, the one above the wing gets wider, so that air can speed up, decompress, and literally suck the wing up into the sky. Now with regards to lift, rotating the wings is okay, but it causes a host of other major problems, and the main one is rotational imbalance. Consider the engine in this helicopter. Its torque is trying just as hard to spin the main rotor as it is to spin the body of the helicopter. Think about all those action movies when the bad guys shoot at the helicopters and the helicopter goes spinning out of control. That's the natural behavior of this vehicle. So something has to be done to stabilize that rotation. And there's 2 basic approaches that have been tried. The first one, like we saw before, is to use a pair of counter-rotating rotors that spin in opposite directions. Like this design with this great figure-8 drive belt. It was the first manned helicopter to achieve flight. Of course, all that spinning mass causes problems. Consider this flying observation post from World War I. It was so shaky it had to be chained to the ground in order not to crash. Modern helicopters tend to use a different idea. This tail rotor is oriented like a vertical fan, and it uses aerodynamic force instead of angular momentum to keep the helicopter's spin in check. Now, this linkage here changes the rotor's pitch. Let's see what effect that has on things. Looking at this animation, we see that changing the angle of an airfoil relative to the wind changes the amount and direction of lift that's generated. You've probably experienced that too, just from waving your hand out the window of a moving car. So this variable pitch rotor not only balances out the torque from the main rotor, it's also used to steer the helicopter. Next problem, how do you actually go somewhere? Well, you might think that just pitching the rotor shaft in a direction would move the helicopter that way. And you're right, except there's one big problem. All the spinning mass acts like a gigantic gyroscope, and it's really hard to change the angle of that. Fortunately, our heroes came up with another idea, changing the pitch of the individual rotor blades as they spin. Remember how changing the pitch affects the lift? Well, watch this. Suppose I'm a helicopter and I want to move forward in that direction. When my rotor is oriented here to the side, I want to pitch it like this, so there's some component of lift that's moving me forward. I rotate another 90 degrees, and now I have to neutralize the pitch. Otherwise, I'd have a sideways motion and go off course. Another 90 degrees, and I pitch the wing down. Again, I'm getting a lift component in the forward direction, even though my rotor's moving backwards. And I finish up my rotation, again with a neutral pitch. It's a pretty complicated motion. You can see it generates a lot of forces and a little bit of dizziness too. In order to make it work, they had to invent a thing called a swash plate. That's the silver disc here that can be pitched up and down, left and right with the pilot's controls. And these links ride along the swash plate and match the pitch of each rotor to its angle. Now, watch the rotors as I move them. I'll adjust the swash plate. And if you focus on this front black one here, right now it's oriented for forward motion. I spin it 90 degrees. It turns horizontal. 90 degrees more. It's pitched up. And I finish off the turn neutral again. Now, given the size, weight, and speed of real rotors, this is one tricky piece of engineering. And helicopter people respect that. You see it reflected in the name they have for this silver nut that holds the rotor shaft together. It's affectionately known as the Jesus nut, because if something goes wrong with this, that's who you've got to call for help. Now today I'm delighted to have an expert helicopter pilot with us, Alex Loeb, who did the stunt flying at the beginning of our episode. Welcome, Alex.
Thank you, Brad.
It's great to have you here. I think the first obvious question is, have you ever seen a Jesus nut fail?
I have not.
Glad to hear it. Hopefully we're not going to see that today. We will see some basic maneuvers though. This is a dual rotor design. How does it actually get lift then with the two rotors? What control do you use for that?
That's just the speed of the rotors, just the altitude control.
That's very simple. And in order to spin it, you have no tail rotor like I showed, so how does this turn?
It makes one rotor go faster than the other one, and the torque turns the helicopter around.
I see. Now this does have the same kind of cyclic as what I demonstrated earlier today, right?
Yes,
so if you want to go sideways or go forward, ooh, scary 3D model. And here's something you can't do with planes. Oh, sweet. Now how do the flight characteristics of an RC model like this compare to a full-scale helicopter?
Well, they're very similar. Most of the controls are the same, and they are real helicopters. They're just real little helicopters.
That's a good point. Is there anything this can do that their big brothers can't?
Well, some of them can fly inverted.
Oh, upside down.
That's right. They go upside down, and
Excellent.
they can stay upside down. And
cool. Can we see that today?
I'm afraid this isn't one of the ones that's capable, but...
Ah, too bad. Well, that's all we have time for anyway. I'd like to thank my guest, Alex. I'm Brad Braufman on behalf of Technology Works. Up, up, and away.